Okay.
Okay, meeting host. Could you also make like Pam a co-host for any reasons she might do that?
Recording in progress.
Unmuted. I can share host disabled participant screen sharing. Could you also make me co-host?
Are you able to share now?
Yes. Okay, cool. Okay. Doesn't drop to. Can you see the screen?
Yes. Turn the one camera.
Can we still see the screen? Okay, perfect. Good.
Okay.
Who's changing the slides?
Yeah, that's perfect.
Perfect.
We're gonna put down the cards. Take it away.
Take it away. All right, good afternoon, everybody. We are the MOSafely social media risk detection dashboard team. My name is Alex Kohler. I worked on the front end and the back end.
My name is Zach Gerhardt. I worked on front end.
My name is Stefania Sanchez and I work on machine learning.
I'm Ryan Doherty. I worked on the machine learning in the back end.
My name is Kenneth Tran, and I work on the database. And these are our sponsors, Dr. Pamela Wisniewski and Ashwak Alsabai. She is a graduate student at UCF. And they work at the STIR Labs, which specialize in social, human, and technological interaction. As of 2018, 95% of teenagers have access to smartphones. This means that a majority of them will end up using social media platforms. And from these individuals, it might have a good benefit of like communications and being able to learn online, but there are also adverse effects such as 1 in 11 teenagers have been sexually solicited online, and 1 in 9 have been a victim of cyberbullying. The current solutions for these problems is currently parental control, direct monitoring, and device-based control and restrictions. And these don't properly address the problem itself, since parents are often inundated with irrelevant information that they don't really need or use, and teenagers feel as if their privacy has been invaded. So our current AI systems that have been developed to try and tackle these problems have a major flaw, in that a majority of them are using publicly available data, such as the Justice Pervert data set. The problem with this in particular is that it doesn't provide an accurate experience of a teenager. This is because this data set is often taken from conversations of convicted sexual predators, along with actors that pretend to be children. So this means that the children aren't truly a stakeholder in the design and implementation of these systems. So MOSafely is an NSF-funded project which is meant to make the online environment much safer for adolescents. Two main components are Instagram data donation, which is our collection phase of data, which works with STIR Lab researchers to assess this data that's usually donated by teenagers. The second component is the AI detection dashboard. So that's actually our senior design project, which allows teenagers to be able to assess their own data and understand what their risks are. So our project is targeted towards 13 to 21-year-olds. And we allow them to submit their Instagram or their Twitter data that runs across our machine learning algorithms, which will give them a visual risk assessment dashboard. And they work on two categories. First is sexual risk, and the second is cyberbullying risk. So our senior design project is the second iteration of its form. This is the calculated monthly budget for our project. It's about $135 a month, assuming about 1,000 users. These costs are spread across some of our services, such as our database, our Lambda functions, and as well as our machine learning component. So for communications with our sponsor, we ended up using Skype for our weekly and bi-weekly meetings with our sponsors. We also use GitHub for our version control of our whole project, along with anything that's related to Stir Labs. We use Dropbox for our sponsors to kind of bring any information in and out. But for our own personal team, we ended up using Discord, Google Drive, and we used a When2Meet to schedule our weekly meetings.
All right, and now proceeding to the system overview, we're going to go a little bit into the structure of the website and how the data flows between various APIs and then back to the user. Come on, I'm just going to step over here. Okay, perfect. So right up top, it displays the users in a visual representation of 3 strangers. Great, right up there. The users then utilize the front end of the website using the web app, which is our EC2 server. That's myself, Zach and Kenny that worked on that. They go ahead and upload their Instagram and Twitter data or Twitter data to the front end of the website. From there, we can kind of follow the pipeline as to where this data goes and how it eventually reaches predictions back to them. So if we follow the arrows from the EC2 web application, we notice that to the left, there's a data upload in which they upload their data and it ends up in our Amazon S3 bucket. So the S3 bucket is basically just like a bucket. It stores the zip files and then eventually images that come back through the image processing function will end up stored in that bucket as well. So any relevant files to the user will be placed in those buckets. So from there, the user data is then processed. There are AWS Lambda processing functions. So AWS in this case means Amazon Web Services, of course. The Lambda functions, we actually have several of them, one for each of the sites and then one for image processing. So we have obviously Instagram and Twitter functions because although the Instagram and Twitter data is formatted relatively similarly, there is some differences that we need to address, hence the need for 2 separate Lambda functions. The image processing function also addresses the processing of those images. And if there is any images within those direct conversations, it allows them to be displayed on the front end eventually. So that parse data, the raw text that's pulled from those zip files, is then pushed towards the prediction API, which as Stefania and Ryan worked on. So that prediction API works through machine learning algorithms and then eventually returns predictions back to the Lambda function. The Lambda function in turn also returns processed images, again, from that image processing function back to the S3 bucket where they're stored for the user to display on the web server. You notice the images going right over there back into the front end. So from the Lambda processing function, once the predictions are returned back to the Lambda, they're stored within the database, and those predictions are then displayed back on the front end on the web app and pushed back to the user.
So this is the old database on the left-hand side, and this is our newer database schema on the right-hand side. As you can tell, we've added a lot more fields to allow us to have more features, along with any future implementations that would be needed.
All right, so with the user interface being completely different from the original version 1 of the site down to our current version 2 of the site, we focused very heavily on a user-focused design matrix. So what we were looking for when redesigning the site, whereas we were looking to take out a lot of the blocks of text because that is a lot for teenagers to read. And oftentimes people just kind of look for buzzwords, things in bold, images, things of that nature to kind of get their information from the website. So we took out a lot of the overly explanatory text on the site and we shifted to a sort of broader bubble button focused approach. So as you notice, we also integrated the MOSafely logo and took away the Stir Labs logo so that we could focus on the broader aspect of protecting youth online and the broader organization of MOSafely. We also changed the color schema from the avocado green of the Stir Labs to the more broad, bright blue and purple of MOSafely. From here, we transition to the login page. So assuming that you're a user logging in or creating a new account, you'd obviously have to go to a login page. So the original is in the top left-hand corner, or just kind of a big blob of text in which you could log into the site. While we primarily kept that same intuitive approach to our new design, we went ahead and added a little bit more color, a little bit more rounded for a safer, sort of cleaner feel over here on the right-hand side for our new and improved login screen. From there, we also proceed to the data upload. So this is kind of the meat and potatoes of how the user uploads their site. It gives them a very brief overview, sort of like a mission debriefing statement as to what they're uploading their data will do for the website and then for protect use as a whole online. From there, we also have an option for them to upload either Twitter or Instagram data as mentioned before. We transition from, again, less text to more image focused approach. So we put the logos of the sites, they're easily recognizable for users, and switch to just one simple line, which is, which social media site would you like to upload your data from? Clicking on either of the Twitter or Instagram logos also displays a drop-down overview of how they can download their data if they don't already know how to do so.
So now onto the risk dashboard. This is basically giving them an overview of the risks that we have flagged for their conversations. It's an at-a-glance type overview. On the left side, we have the original website that has the overview on top of the conversation list, which is all the conversations that they have uploaded. But we did switch it and split those two pages in order to kind of streamline the process. Once they get into the conversation page, we want them to stay there. So on our right side, we did update the risk assessment dashboard. With each risk, there is a percentage associated with how many conversations have that particular risk associated with it. They can click on each one of those cards to organize the conversation list by that particular risk. And then they can go ahead and click on into the conversations list, which on the left side, again, we have a little, the original first iteration of the conversation view. You'll notice the list of conversations is a bit longer with the messages being a little smaller. Since we did implement a message level risk detector, we went ahead and expanded on the conversation side of it or the message side of it. And so on the newer version of it on the right side here, we wanted to go ahead and make sure that we made it familiar for the users to look like a social media platform, something that they're used to using. So keeping the conversation small on the left side, keeping the actual conversation larger on the right. And I want to point out that we do have all of the risks flagged by icons. We do provide them with a legend so that they know which icons mean what, as well as tooltips, which I can show you during the demo. Another thing I want to point out is going to be the unconfirmed risky messages. So since we want users to provide feedback on the risk assessment that we provided, we want to make sure that they know how many are left and kind of get them to work towards that goal of completing each conversation. And so whenever they do provide feedback, like I said, we have a legend on what each risk means. Each icon is color coordinated so that at a glance you can know which risk is what. On each message, there's going to be a confirm or deny for messages that have been unconfirmed. So they can check it saying that that one's good, or they can hit the X so that it would bring up the message feedback, or they can provide a detailed reason as to why the risk is not what we thought it was. The whole point of this is so that we can retrain our models later on, and we'll use that feedback again to train those models. And we also have a conversation level feedback as well, where users can change what relationship they have with the user. That way, again, we can train it to be a little bit better, because if someone is, say, dating someone, then we know that more sexual risks may not be sexual risks, but that's for training growth.
So now onto the machine learning. Do you mind, please? So again, this is the second iteration of this project. As part of the first iteration, the team inherited conversation level risk detection algorithms from the graduate students at STIR Labs. So in this iteration, we developed two new message level risk detectors for cyberbullying and sexual risk. Overall, though, the conversation level models categorize the risks for cyberbullying, sexual risk, images, links, and relationship level. No worries. So those conversation level models work the same as before. They look at the entire conversation and then for each category determine if it is risky or not. The message level models work a little bit differently. They are a two-stage classification system. So first, it will look through each message and determine if it is risky or not for cyberbullying and sexual risk. And then once all of those risks are compiled, it will calculate the risky to safe ratio in a conversation. And if that ratio is more than 10% of the messages, it will classify the entire conversation as risky. This threshold of 10% is something that can be easily changed using that user feedback to be more sensitive or less sensitive depending on what the conversations are classified as.
Okay, and for the machine learning API, this is our web server that hosts our saved machine learning models. We've first taken each conversation from the Lambda function one by one in a formatted JSON file. That then we evaluate the conversation level risks for both the cyberbullying and the sexual harassment on the entire conversation. We also take our given relationship models and image risk models and run that against the entire conversation at the start. And then finally, we use our new models, the cyberbullying and the sexual risk classifiers, return a list of confidences for our model in each of its predictions against each message. For the predictions, we would test our machine learning API using Postman. We have an example on the right-hand side of it would take in messages in a list like that, and it would return either a string for the conversation level models, such as the cyberbullying would be marked as bullying or non-bullying, and for the sexual risk, it would be marked as sexual risk or non-sexual risk. And then we have examples of the arrays for each message, which is referred to by our Lambda function, put it back into the database correctly.
So now into the development of these models, the first step was analyzing the data that we had. So as part of a research project, the STIR Labs collected over 6 million real messages from teens. These are Instagram messages, and this is what we use to curate specialized data sets for cyberbullying and sexual risk. So we did this by looking at specific risk labels for each category. So for cyberbullying, that was harassment, hate speech, self-injury, violence, or threat of violence. And then for sexual risk, that was sexual solicitation or messages, nudity, and porn. So once we had those labels and those messages, we had to go through and manually clean them further. We noticed in our first couple testing of our models that a lot of our false positives and false negatives included messages that were contained hi, hello, how are you? And these messages are not inherently risky, but they are the start of messages, or excuse me, conversations that contain risk later on. And so they were classified as risky because of that. But we decided to focus our risky data sets on specific messages that contained explicit risk instead of messages that contained risks that needed outside context. So from there, we supplemented our data sets with an equal number of safe messages, as you can see in the little pie chart right there. And this is what we use to train and test our models. From there, once we had these data sets, we did standard natural language reprocessing of the text. So that was tokenizing, lowercasing, removing non-alphanumeric characters, removing stop words, and then going into tokenizing and vectorizing the words to make them understandable by these models. So for the word embeddings, in order for these models to understand the text again, they need to be turned into vectors. So we experimented with different kinds of vectorization methods to see which ones would perform best with our models. First, we started out with simple methods like count vectorizer or TF-IDF, which just use basic counting or statistical properties to create numerical representations. But these did not provide our models with enough information to be able to predict well on our messages. So we eventually moved on to more advanced methods using neural network-based vectorization models, such as word2vec. The way that word2vec works is that it will take in a corpus of text and then it will vectorize the words based on their relationship to each other. So more similar words will have a more similar vector. And this did work well, but we faced some issues when presented with words that were not a part of the original corpus that word2vec was trained on. So word2vec was not able to recognize these words and would produce a garbage vector, and that would have a negative impact on our accuracy. So now Ryan will get into the other method that we used.
All right, so the final method that we used for creating our word embeddings was the Google Research's BERT model. And more specifically, their improved version called the Electra model. These tackle the problem of word2vec does not care about sentence level context. For example, in the two sentences, a man robbed a bank, and another sentence where they would say a man had a picnic by a riverbank. The word bank, despite having very different meaning in each context, will have the same exact representation in a word2vec model. Electra and BERT do this differently because they process the embeddings for each word by paying attention to all of the other words in a given sequence, which in our case is a message. Electra improves on the training of the BERT model by using an overall like more of a generative adversarial network type of training instead of what BERT uses, which is just blanking out a word and predicting that word. The discussion of that may be a bit beyond the scope of this presentation. It would take a lot of time. This Electra model using this improved training technique achieves unprecedented accuracies on some many natural language processing benchmarks like GLUE, while also using little compute power, which we can process on our own machines. Next slide. We use transfer learning on top of both the Word2Vec and the pre-trained Electra models. We used a pre-trained Electra model from TensorFlow Hub from Google. This was integrated into our model, and we put a classification head on top of that model. We experimented with different types of classification heads, like we used just simple dense neural networks, and we also tried bidirectional LSTMs. We also did the same on top of a Word2Vec model as more of a baseline because the Electra model always outperformed it. For the hyperparameter and architecture tuning, we use the Keras tuner library to experiment with many different model architectures and many different hyperparameters. Using their hyperband algorithm, we trained a large number of variations of models for a very short amount of time, and we would put them in like a sports playoff brackets against each other. For example, in the first round of each run of the hyperband tuner, it would run like the models for like 1 or 2 epochs each, and then the winner within that bracket will go on and be trained longer. And eventually, like in sports playoff bracket, the best model will become the winner. We further trained this winning model with and then fine-tuned it against our data sets to achieve the best possible accuracies. In the end, a deep neural network had the best accuracy as a classification head. Most of our efforts were focused on these bidirectional LSTMs and dense neural networks. The bidirectional LSTM with a couple of dense layers, batch normalization, and dropout regularization for most of our senior design 2 had the best accuracy. However, more experiments at the end with different activation functions, different sizes of the dense neural network made it come up with the best testing accuracy overall. So that dense neural network used thousands of neurons that decayed as the model went along, like it would decrease by powers of 2 until the final classification. Here's an example of the architecture of our best message level sexual risk classifier. We will take in a raw text as an input layer, and it would be pre-processed by the TensorFlow hubs. They have a BERT pre-processing, which applies as well to Electra. It creates all the needed fields, like it creates the, it tokenizes and does all the natural language process, like pre-processing that we discussed earlier. And it also creates the BERT and Electra specific masks, such as the attention mask, which determines where in a sentence to pay attention to. We then feed that input into the Electra embeddings layer. This is our pre-trained Electra model. It is pre-trained on the general English language for much more time and with much more compute power than we can ever manage. So it is already very close to converging. And then on the right-hand side, we have the classification head that takes in input from this Electra embeddings layer. Our best classification head after experimentation ended up being a deep neural network with 5 dense layers and some dropout regularization. We experimented with more regularization, however, it never, it hurt our testing accuracies and generalization more than it helped. So this amount of regularization with the built-in regularization of the Electra model was enough. For the training of the classifiers, this is where we probably got our biggest increase in our accuracy. From the best hyperparameters and architecture, we build that model further, and then we fully train it over 20 total epochs. We start by freezing the weights of the Electra layer as it is already pre-trained on the general English language, and Meanwhile, the classification head is randomly initialized. So we just let it, okay, so we just, we let it train the classification head just against the pre-trained Electra weights for a while, just so that it becomes close to converging as well. We then reduce the learning rates and then fine tune the Electra model because now both the classification head and the Electra model are close to converging. We reduce the learning rate and then just to get that little bit more accuracy as we could. And then we've further trained that. We do that for 15 epochs afterwards, and then we further reduce the learning rate every 5 epochs according to a learning rate scheduler.
Can I ask a question? Yeah.
Sure.
So this is not the typical way in which people are using the BERT for classification, right? I have never in my life had seen LSTM on top of BERT.
Yeah, it worked pretty well for a long while, but just a simple dense neural network ended up being the best after some more classification. We experimented with different things. We just went wild at the start of scene design too. Like I don't think I've also seen it either. However, it did perform very well for a while. But
So what are you feeding into the LSTM?
we were feeding in the sequence outputs from the Electra model. It creates the embeddings for each word within a sequence, and that 3D output is being fed into the LSTM.
Okay.
Yeah, I'll pass it on now. After experimentation with many different optimizers, we tried stochastic gradient descent, we tried different versions of Atom, but the Atom optimizer with Nesterov momentum gave us the best generalization and validation accuracies. We also used a few callbacks within our training, such as early stopping, which ends training early if the model starts to overfit, and we chose to early stop based on the validation binary accuracy. It will also restore the best weights if it does start to overfit and has to stop early. So we don't use the overfit model. We also use the TensorBoard callback to allow us to have some comparisons to the earlier runs of the model, and to also have more information about how our model trains. And it gave us some good graphs for our presentation. We also use an 80-20 train test split, and we use 15% of that training data as validation. Here's an example of our binary accuracy over time for our final sexual or cyberbullying classifier, our message level classifier. The orange line is the training accuracy. As you see, it gets very accurate over time, as with what happens with training accuracy. And the validation accuracy, due to our regularization and the built-in regularization of Electra, slowly increases over time. Then here's an example of the loss over time in a model that does not have early stopping enabled. As you can see, this converges very quickly. These graphs are generated after the classification was already trained. So they converge very quickly, and without early stopping, we can see that the validation accuracy, the validation loss, does increase over time, which indicates a lot of overfitting. So early stopping would stop this pretty early, around epoch 3 or 4, and that's what we ended up using in our final models.
So to evaluate the performance of our models, we used a classification report and a confusion matrix. Over here, you can see the confusion matrix for our best performing cyberbullying model. So most of our predictions fall into the true positive or true negative categories, which is exactly what we were looking for. And then we use the values that fell into the false positive and false negatives to go back into our data, see where we needed to maybe supplement with more safe data, more risky data, clean out certain messages like how we mentioned before with the hi and hello, and overall just reevaluate where we could improve in the next run. So this is a classification report for our best performing sexual risk model. It just breaks down precision, recall, F1 score, and accuracy for risky and non-risky predictions. So as you can see, we have an overall F1 score of 87%, recall of 89% for safe messages, and precision of 85% for save messages as well. So this is just an overview of all of the models that we have and their performance. Our models that we developed are highlighted in purple. So we wanted to make sure that our models were performing at least as well as the models that we inherit from the graduate students, because we were planning on using these two things in tandem. The images and links that I mentioned before and the relationship level work separately from the message level. So lost my train of thought. I'm so sorry. But yeah, this just provides a breakdown of all of our accuracies and F1 scores. You can see that our cyberbullying model outperforms the cyberbullying conversation level model with an 82% accuracy versus a 68% accuracy. And then our sexual risk model is almost as good as the sexual risk conversation model with an 87% accuracy versus an 89% accuracy. So once we have these models, we use the Keras library to download them, as well as their associated tokenizer. It's important that we also save the tokenizer for the model. So that way, when we ran predictions with user data, these messages were tokenized in the same way, and the model would be able to work with that tokenization. And then these models were uploaded to the machine learning API to be used live on the site.
All right. So for testing, we actually had a variety of different methods of testing. First being on the front end. So we participated in MOSFest, which is shorthand for Mozilla Festival, a way for us to connect with actual professionals within the industry, as well as teenagers attending sort of like a virtual fair convention of sorts, in which they would demo a lot of projects regarding youth safety online. So we were lucky enough to be one of those demos. So you can see right up there, that's us on Zoom demoing the live site. We also tested on different screen sizes to ensure consistency across varying displays. And we tested on multiple browsers, including Microsoft Edge, Google Chrome, Mozilla Firefox, etc. As for the result page, we had a lot of different types of testing that we had to ensure to make sure that everything was displayed the way that we wanted it to. And that includes sort of stress testing the site with various degrees of conversations, risks, messages, as well as different numbers of messages, larger files, smaller files, and then different types of column headers to make sure that everything was displaying regardless of the data being inputted into the front end.
For the machine learning and the Lambda testing, we did direct model performance evaluation by having actual teams use our machine learning API with a website we created for STEM Day here at UCF. We created a website called Bully Me Machine Learning API, where teenagers could put in a message, and instead of going through the whole process of downloading your data and uploading it to the site, this directly could talk to our machine learning API, and it's allowed students to bully our AI, and it would give them feedback immediately over whether their messages were marked as risky or not, according to our classifiers. We also did some standard model performance evaluation, just using the statistics that we got from our classification reports and with our own testing. We tested the machine learning API itself using Postman, just to test how our models are being hosted and to make sure everything was working correctly. And we finally tested the whole stack of the Lambda and the machine learning API by just uploading Instagram and Twitter zip files to our website. During STEM Day, here's a picture of the Bully Me machine learning API website. They put in a message. This was from an actual teenager. They said, "Your dad left for milk." And this was one of our earlier models. Our current models do not mark this as sexual harassment. However, our current models still do mark this as risky for cyberbullying, which the team agrees with. And on the right-hand side, we have a picture of actual teenagers using this Bully Me machine learning API, and we got a lot of feedback. We had a lot of examples of messages of how teens talk and what they would say to bully someone. And we use this for further data augmentation, and which is fed into our models that we use now.
Okay, so this is great in sort of an abstract concept, and we've gone through this on a very high level, but obviously we need to kind of show you how it works in a live demonstration.
Okay. So,
Thank you so much.
Okay, so it will be.
Which tab am I looking
Up there.
This one? Oh, this is your screen?
This is the second
Oh,
one.
that is the screen, okay.
Yeah, that is.
Okay, sorry. All right. All right, well, welcome to our homepage. This is going to be the first page that teenagers would see when they are landing on the site. For this, I'm going to be envisioning myself as just a regular old teenager who has never been on the site, but has heard about it and ideally would like to upload some of my data so I can assess risks online. So this is going to be our homepage. We can also click here to get started immediately, but I think it's good to note the frequently asked questions up here, along with some help resources. So we're going to go ahead and click on that. We have some frequently asked questions regarding usage, including browsers, devices, privacy policy, instructions, and then also troubleshooting. And then if we are a teenager who has recently realized that maybe there's some sexually risky or cyberbullying risks in our messages online, we can go ahead and click the help resources right up here. And it'll give us a link to some mental health resources, suicide prevention resources, and then also the child abuse hotline, just in case there is an active emergency going on, they have a way to seek help. So we can click home. All right, so this is kind of our mission statement down here. It tells the teenager what's going to happen with their data. So our AI will flag potentially risky messages from the social media data that you upload, and you can provide feedback to make our system even more accurate. So it detects cyberbullying, sexual harassment, and then also inappropriate images. Let's go ahead and click to get started. Perfect. Okay, so this is going to be our login and landing page. It has pretty much the same overview as the original homepage. Today, we're going to go ahead and both sign into an old account that already has some data supplemented into it, as well as demonstrating a fresh account and how we upload some data. So I'm going to go ahead and create a new account for the purposes of this demonstration. So I'm just going to make a demo email. That's demo email at demo.com. Test demo. So you can see our lots of test accounts there. Okay, so we're going to go ahead and create a new account under the name of test demo. Perfect. All right, I'm going to go ahead and save this just for fun, and we can hit sign in. Lovely. So as stated before, this is going to be our landing page and kind of debriefs the teens on what's going to happen with their data and the benefits of providing their data to the site. So as an overview here, it provides the teenagers with useful information regarding potentially risky online interactions, as well as helping train our artificial intelligence. And then on a very broad perspective, we put a little bit of the responsibility back in the teenagers' hands by assuring them that by donating their data and providing feedback, they're not just helping themselves, but helping all young people safely engage online. Let's click to get started. Okay, so we have a terms of service and a privacy policy right up here. This just asserts the user that we don't hold onto their data for more often than it is necessary to give them predictions and the information back. So we'll click agree to these terms of service. Perfect. Okay, so we have two options here. Which social media platform would you like to upload your data from? So you can see very clean. We don't really give them a lot of extraneous text until you click on either one of these boxes. So this will prompt some drop-down information on how to download their data, including the different ways in which they can receive their data from these sites, as it does differ a bit. Let's go ahead and upload some Instagram data. Clicking on this button, select zip to upload.
Demo folder.
Demo folder?
Right. Starts.
Okay. There we go. So that is an Instagram file that we downloaded from a test Instagram account. Clicking submit will upload the data to our site and drop it in the S3 bucket. So we'll be redirected once the upload is complete. It does take a little bit of time for the ML API to kind of parse through the messages, but as we can see, refreshing the page or going to the risk detection dashboard again, we'll update the results as we go along. As you can see, the cyberbullying is going up a little bit. Clicking on the conversations will give you a brief overview of the conversations tab. And now I'll pass it off by logging out over to Zach, who will demonstrate a live login account that already has some test data put into it.
Okay, so we're gonna go ahead and take a look at what happens after the user's data is uploaded. So again, this is going to be an at-a-glance overview of the risk associated with their conversations. So we want to make sure that they can see, how many messages are considered risky, even between the sexual and the cyberbullying. And also want to encourage them to continue to give us feedback because again, they are stakeholders in this project. We want them to be empowered to provide feedback so that other teens can have a safer experience online. So we'll go ahead and click into the conversation by clicking on the cyberbullying card because it will organize it by that risk. Just to show you here on the left side with those conversations, again, the icons indicate the bullying risk. We can scroll down and see that there is no bullying risk here at the bottom. So sorting there is working as intended. And so once a user lands here and they're looking at their conversations, we have a couple things to let them know as to what is going on the screen. We'd like them to be able to click on a conversation to see the messages and so that they can go to each message and provide feedback on the particular message level risk that we found. Up top, we do have that legend that I mentioned earlier so that again, at a glance, they can know what they're looking at. So we'll go ahead and go into this Luis Rivera. And we can see that some messages are marked in that red bubble. That is an unconfirmed risk. And you can see in the top right here, the unconfirmed risk number, and as well over here in the conversation list view. So they have a goal to work towards. So the idea is to get that down to 0 for each conversation. So for some of these, you can see here, this one is marked confident, but if the user does not agree that that one is risky, we can go ahead and hit X. We can go ahead and provide some feedback and say, I like to salsa. We can save that and okay, well, let's see if we can go ahead and check this one as, well, we'll go ahead and continue on. Over here in this Twitter data file here, we can see that we do have a image marked as risky. So again, the user can see the confidence level of that message and provide feedback on as to why that message is not risky. And for the whole conversation, they can also provide feedback on that as well, because again, we do have a conversation level risk as well as the message level. And so if the user does need to provide more detailed feedback, they can go up to the conversation feedback and say that this particular person didn't bully me and doesn't have image risks, as well as changing the relationship that they have with the user so that we can better train our models down the road. They can also sort the information by different types of risks so that they can better work on the problems that they want to focus on. Maybe they particularly have a cyberbullying happening going on or a sexual risk thing. So they can go ahead and organize it by that. And again, it will organize those messages accordingly. So we will go ahead and switch back to the presentation.
All right, so as we said before, we are the version 2 of a version 1 team. So as a summary of our personal contributions throughout the semester, we added several new features to the website that were not previously available in the first iteration of the project. Namely, Twitter upload functionality was not included in the first version of the project. During the beginning stages of the project, we sorted through which websites would be the best to use as upload functionality for the user. So they have an option of selecting 1 out of 2 different sites to upload their data from. We picked Twitter because the JSON is relatively similar to the Instagram formatting, although it still needed to be tweaked a bit. We went ahead and added trained message level risk detection, which, as we stated before, the models were only previously conversation level risks. So these message level detections actually go through every single message and will return risks on the individual messages presented. We also added enhanced detailed feedback solution for users to correct risks. Previously, it was not intuitive as to how the users would submit feedback, and so people often just wouldn't. With our solution now, it's a lot more clear for the user to be able to give that feedback, and in turn, we can train our data models. And then we also have a streamlined sorting of conversations by either conversation or message level risks, which allow the users to seamlessly work through the data. And if they're searching for something particular that's alarming to them, they can go ahead and just sort it by message, either sexual, bullying, etc.
And so again, we did have a more user-focused design implemented. We transitioned to that user design focus by creating a more modern, familiar look for the social media style that we're going for, again, with that conversation view. looking more like a familiar like Instagram or Facebook style conversation list. We also change up the colors from that Stirlab green, you can see in the top right here, and change it to that MOSafely purple, provides a little bit more of a familiar feel to it. To me, the green kind of just says that go away type deal. And then we revamped the risk assessment feedback to be a little more streamlined, as Alex was mentioning just a moment ago, making it simpler for the user to provide that feedback and be a little more detailed on why they would change the feedback that we found in the risks.
Of course, as stated previously, since this is a version 2, we actually inherited not only conversation level models and a very basic website, but unfortunately also bugs and security issues. So that was our first step when inheriting this project, was to kind of squash those so we could proceed to add new features. One of those, we updated our site to use HTTPS instead of HTTP, so as to encrypt plain text throughout the internet. So that way we're not setting plain text passwords to our site. The Instagram Lambda function was riddled with processing errors and therefore needed a lot of TLC to get up and working. For example, special characters would actually not return predictions from the only API model, and overall just need to be fine-tuned to ensure that every single file would work. The image downloader function was completely inoperable at the time of our inheriting it. So when we received that function, we had to put a lot of work into making sure that it not only worked with Instagram data, but also to sort through the file structure of Twitter data to ensure that it could pull the correct images and sort and assess them with the correct conversation and implement them in the messages. The logout function was unfinished, while the login function was functionally incomplete. So we had to implement the logout function as well as added a login function that actually like took in all the passwords that the user made, because at certain times it would just reject certain passwords and not give any feedback as to why that was. And then oftentimes a file would often stop the progress bar at 33% and progress no further. There was initially sort of a 0 to 100 sort of progress bar. It would just stop at 33 and that was it. You wouldn't see anything else. So we implemented a sort of spinning progress bar and also ensured that the user could upload their file seamlessly without any errors.
For the challenges of our project, we had some technical difficulties with the Amazon Web Services function, Lambda functions, as we mentioned in the previous slide. And we also had a big problem getting access to the research data for our message level classifiers. We had to get approval from the UCF's internal review board for ethics because the sensitivity of this data is very important to the STIR labs. When me and Nia finished the training in Senior Design 1 in December, it still took a few months for the internal review board to approve our us to actually get access to the data. So we didn't actually get access to the data, so we couldn't start working on the machine learning in any significant way until about midway through February. So we've only had like about 2 months to work on the machine learning stuff.
As for lessons learned, it's safe to say that this project was a huge learning experience for all of us here. In terms of time management, it's obviously difficult to manage the schedules of 5 different people. So we learned early on to prioritize this project, prioritize each other, and then also make time to communicate when we couldn't show up to meetings and other events like that. Team management is also something that we learned pretty quickly. We made sure to keep each other accountable for our work and keep our progress organized. Adaptability was also something that was very important to us. Our main priority throughout this project was meeting the expectations and desires of our sponsors. So when those expectations changed, we also had to change. And lastly, we all saw a very big improvement in our technical skills as a result of working on a project of this caliber. So to summary, during these last 2 semesters, we developed new machine learning models for cyberbullying and sexual risk, as well as revamped and redesigned the risk detection dashboard, all with the ultimate goal of creating a safer place on the internet for youth.
Thank you.
Thank you. Very nice.
So since we don't have that much time left and Ashwak and I have been able to talk to them all semester for actually 2 semesters, I'll let the other committee members have this time for their questions.
Questions?
Yeah, I don't have a question. So in the risk report, like there are buttons that users can report whether they think it is, risky or non-risky, right? So what if like a message is labeled as, is classified as not risky, but the users think it is risky? Is there a way
Sure, so,
for them to report?
yeah, I can show you here.
Yeah.
So like, let's say this message here that says yes, if they want to
Oh, I
edit it,
didn't
they can
see.
go ahead and edit that.
Oh, I
And
see.
submit the feedback there.
Okay, I see. Another question is related with the testing you have on the STEM day, right? You have
Mhm.
a couple, like how many teenagers try this beat? Or what is it? Yeah.
I believe each session had about 20 people, if I remember correctly. So there were a couple sessions of the day. I would estimate over 50 to 100
Okay.
teams.
Okay.
I'm wondering if she's referring to the Instagram data donation data set in which the classifiers were trained on, like how many participants there.
Oh, no, I'm asking for the STEM day testing.
Okay.
Yeah. So because I wondered how they feel, how they felt about the system. Like, do they think the classification or the prediction were accurate or not?
Like Ryan mentioned, this was an earlier
Okay.
model, so there were a couple bugs with it.
Okay.
But overall, they were excited to interact with the website, and they were pretty pleased with the majority of the predictions that they
Okay.
received back.
I'll also add that the whole purpose that we're building this dashboard is so that we can do a more formal user study next steps to do an evaluation of the algorithms.
Oh, so that's a nice step. Okay. And last, sorry, my last question, or it's more about a concern. So in the beginning, you ask the users to upload their Instagram data, right? So that's basically the entire Instagram data, or
Yes, like you can request your data
Yeah.
from Instagram or Twitter.com, and it'll contain everything that has to do with your Twitter account or Instagram
Okay.
account. So every post, every message.
yeah, I feel like, well, if I am a user, I may be a little bit hesitant because, not all my Instagram data are, risky, right?
Yeah.
So it would be better if I can just upload a segment, for instance, a particular conversation from my Instagram. I just paste
Yeah.
there.
That could be a future iteration of the project, where because right now these files need to be formatted pretty specifically for our stuff to work on it. So we'd have to have some kind of program that the user can use, because asking a teenager to edit a JSON file to remove their messages and stuff could be very complicated very quick for anyone but a CS professor or students.
What I will say in addition to that, though, is that the way that the Instagram data in particular is formatted, that is separated per user. So maybe you don't want to add a conversation with somebody. You could in theory go into your zip file, but you would have to have knowledge of how to do that. So if the user does have that knowledge, they're more than welcome to. Twitter is a little bit more condensed into one big file, so I would not recommend doing that. But if with Instagram, then you have that option.
And on the FAQ page, we do have some general guidelines as to folders and files in the zip folder to not remove or not touch at all for Twitter and Instagram. So if they do decide that they want to remove certain messages, they do have a guideline of what absolutely cannot be removed in order for our website to work on the data.
Yeah, and this also has to do with why we had to get the internal review board certification before we could work with the data, because of how sensitive it would be with most of these files containing everyone's complete information.
Thank you.
Yep.
Another question.
Hey Pam, I have a really quick question here. Are you gonna need a version 3 of this, or?
I'm not sure yet. I think Ashwak's going to do a user study for this. And we need to do our own iteration of some design improvements. So that's to be determined.
Okay.
I mean, they did a good job, and they did what they were told. So a future iteration isn't a reflection on them.
Yeah. Well, as you know, I'm always looking for next semester's projects.
Yeah, I mean, this might be one, and so Ashwak and I need to kind of do a one-off to figure out like what the next step is before we do the user study.
Any more questions about maybe the machine
A
learning?
very quick one. You had a slide in which you were saying that you were filtering the messages for the training data.
Um,
And I was a little bit surprised at the amount of filtering which happened, like you started with
This might be yours.
how
Yes.
much, yeah. So 6 million messages to down to 100,000 messages. Ooh.
Yes.
This-
That's for a couple of reasons. A lot of the messages were not annotated, and that was something that was really important. We had to make sure that they had some sort of risk label attached to them. The other part of it was that a lot of these messages didn't contain risks at all. So the ratio of risky messages in that larger data set was not very large to begin with.
That is,
I'm gonna interrupt now since we have another group waiting. We're a few minutes
Nice.
over. So, wait, thank you so much, faculty.
Yeah, thank you.
Thank
So,
you
guys.
so much.
this form,
Yeah.
can I fill later and scan it? and email?
Yeah, that'll be fine. All right, thank you.
Thank you very much. Thank you guys so much for coming.
Thank you.
All right, thanks, team.
Thank
Thank
you.
you,
so
Pam.
much.
Thank you,
Thank
Ashwa.
you. Thank you, Ashwa.
Thank you,
Thank you,
Ashwa.
Ashwa.
Thank you, Pam.
Bye.
You guys, I thought you guys did a really good job.
Thank you.
Thank
so
you.
much.
Very good.
Thank you, thank you.